Welcome to our quantum deep dive. Today we're going to be looking at what sounds like science fiction, a perfect mirror image of our universe. A substance so exotic, so volatile, it completely annihilates on contact with anything we know. We are talking about antihydrogen. You can think of it as a ghost particle that just might hold the answer to why we exist at all. This entire deep dive, by the way, is based on a really fascinating essay by Yurgo Schnepphat.
So, here's our game plan. We'll start with the basics. What exactly is this mirror version of matter? Then, we're going to explore the incredible ingenuity it takes to build and trap something that really shouldn't even exist in our world. And finally, we'll get to the biggest question of all: how this fleeting, ghostly substance could solve the ultimate cosmic mystery of why our universe is here and why we are too.
Okay, so to really get our heads around this, we need to start with a simple but truly profound idea.
Just imagine for a second, a perfect reflection of our reality. A world that's identical to ours in almost every way, same physics, same forces, same kinds of atoms, but with one really fundamental property just flipped on its head. That, in a nutshell, is the strange and beautiful world of antimatter.
And here's what that actually looks like. Let's take the simplest, most common atom we know, hydrogen. You've got a proton at its heart with a positive charge, and it's orbited by an electron with a negative charge. Simple enough. Now, its mirror image, antihydrogen, is the exact opposite. It has a negative antiproton at its core, and it's orbited by a positively charged particle called a positron. Same mass, same properties, same behavior, just a flipped electrical charge. It's a perfect mirror.
Okay, but here is the dramatic, and I mean dramatic catch. Matter and antimatter absolutely cannot coexist. When they touch, they don't just collide, they annihilate. Their entire mass is instantly and completely converted into a burst of pure energy. It's exactly what Einstein's famous equation, E = mc², predicts. It's the most efficient energy conversion possible in the universe. And then, poof, they're just gone.
So think about that. If it just vanishes on contact with literally anything in our world, the air, the walls of a container, you name it, how on earth do you even begin to build it, let alone study it? Well, that is one of the greatest challenges in all of modern physics.
The journey to actually capture antimatter was a really long one. And remarkably, it didn't start in a lab. It started on paper, with Paul Dirac's quantum equations back in 1928. It then took decades of breakthroughs, from spotting the first antiparticles in cosmic rays and accelerators, to finally, in 2010, the ALPHA experiment at CERN, managing to trap complete antihydrogen atoms for over 15 minutes. That was just a monumental achievement. It meant we could finally study them.
So the recipe for making antihydrogen is just mind-bogglingly difficult. Okay, first, you use a massive particle accelerator to smash protons into a metal target, which creates just a handful of antiprotons. Then you have to catch them and their positron partners in what are basically these powerful magnetic bottles. Then you use lasers to cool them down to almost absolute zero. We're talking colder than deep space, just to get them to slow down. And then very, very gently, you try to get them to combine, all while making sure they never, ever touch the physical walls of that container.
Okay, so now that we can actually hold on to it for a little while, we can finally ask that crucial question. Just how perfect is this mirror image, really?
Well, so far, every single test we've been able to run confirms what our theories predict. The mass, identical. The quantum property known as spin, identical. The only measurable difference is that flipped electrical charge. You know, this near-perfect symmetry is a cornerstone of physics, and antihydrogen is our most precise tool yet for putting it to the test.
And this perfection, it extends all the way down to the quantum level. Now, this formula might look a little complicated, but all it does is describe the specific energy levels that an electron, or a positron, is allowed to have in an atom. Because the mass and charge values are identical for both, the math works out perfectly for hydrogen and antihydrogen. And that leads to a really profound prediction. They should both absorb and emit the exact same colors of light.
Right, and when the scientists at CERN finally measured it, the result was just staggering. They zapped the antihydrogen with a laser, making its positron jump from the lowest energy level to the next one up. The frequency of light needed to do that, it matched the value for regular hydrogen with the precision out to 15 decimal places. I mean, as far as we can possibly tell, the mirror is absolutely perfect. But here's the thing. This very perfection, it leads directly to one of the biggest, most fundamental paradoxes in all of science. And this is the central mystery.
Our best theories tell us the Big Bang should have created equal amounts of matter and antimatter. But if they're truly perfect mirror images, they should have just canceled each other out completely in a flash of light, leaving behind a totally empty universe. The fact that you are here listening to this, that the Earth exists, that stars and galaxies exist, well, it just shouldn't be possible.
Yeah, this whole puzzle is called the baryon asymmetry problem, and it's one of the biggest unsolved questions in physics. The leading theory is that for every billion matter-antimatter pairs created in the Big Bang, there is just one extra particle of matter that survived the annihilation. So the great hope is that by studying antihydrogen with insane precision, we might find a tiny, almost imperceptible crack in that perfect mirror, some subtle difference that could explain why matter won the cosmic lottery.
And if that wasn't already mind-bending enough for you, there's another, even wilder question being tested right now. Does antimatter fall up? I know, it sounds crazy. We assume that because it has positive mass, it should interact with gravity just like normal matter does. But no one has ever actually seen it happen. So experiments at CERN are designed to do something really simple. Just let go of some antihydrogen atoms and see which way they fall. Answering that question could change everything we think we know about gravity.
So where does that leave us? What's next for this mirror matter? Well, the challenges that lie ahead are just as immense as the possibilities. Now let's be absolutely clear about something. We are not going to be fueling starships with this anytime soon. Creating antimatter is one of the most inefficient and wildly expensive things humans can possibly do. We're talking a handful of atoms per hour, and the challenges of storing it or moving it around, well, for now, that is pure science fiction.
But the real value here isn't as a fuel source, it's as a tool, a revolutionary new kind of tool for fundamental science. The incredibly unique, stable properties of antihydrogen could let us build the most precise atomic clocks ever conceived, or create sensors that can probe the very nature of gravity and space-time. Its true potential is in helping us answer those deep, deep questions about the universe.
And in the end, that really is the story of antihydrogen, isn't it? By painstakingly building a ghost from a universe that could have been, we are really just trying to understand why our own universe exists at all. It's a key to unlocking the secret of that profound asymmetry that allowed for our own existence.
From the purely theoretical math of Paul Dirac to the unbelievably complex experiments at CERN today, the story of antihydrogen is really the story of our human quest to understand the very fabric of existence. It forces us to confront the deepest questions about symmetry, about reality, and about our own place in the cosmos.
We hope you enjoyed this deep dive into the universe's mirror image. It was based on that great essay by Jörg Owe Schneppat, and you can explore more of his work at schneppat.de. Thanks so much for joining us. Goodbye.
Schneppat.de is a private project by Jörg Owe Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.